I would like to uh, cover Chapter 3 on database systems, which is about the basic relational model, or we call it flat relational model, in which we'll consider some concepts like the relational data model and its constraints, and also the relational database schemas, and there is some operations and transactions like update and delete and insert operations. And also we will consider how to deal with this such violation on these constraints. First, I would like to uh, shed lights on the historical background of the relational model. What is the relational model? The relational model is a database model that is based on relations. That means there is a lot of entities and there is a relationship between these entities that constitute a mini world. The first time people know about this model was back in the 1970s. To be exact, in June 1970, but there is no implementation until early 1980s. That means the real implementation of this model came to existence to be like a decade after its first announcement by Cod, who was publishing a landmark paper in June 1970 from IBM company talking about this model. But after that, after 1980s, it has been implemented in very large number of commercial systems and adopted by a lot of organizations, specifically big companies and government departments. Of course, before that, there is a model which is called hierarchical and network model, which is based on file systems. The relational model concepts, there is a lot of concepts that we need to talk about in the relational model. One of them is a table, which is constitute of rows and columns. The table represents a collection of related data values that contain facts that correspond to a specific real-world entity or relationship. Also, a row, it is called a tuple in relational model concept. A table has to have a name and has to have columns. So each row is a set of attributes that constitute that row. In relational, in database as general, there is some concept that you need to understand. These concepts, for example, entity. Entity is a concept that we use when we talk about the relational model methodology, which is similar to the concept relation or a table. In file system, we call it a file, which contain information. But in database system, it can be called a relation or a table or entity when it comes to design. Again, the row is a record, of course, but also the concept tuple is used to refer to this row. Another concept is called attribute, which is can be used interchangeably with the concept field or column. The column, attribute, and field are the same thing in database. The relational model, as I told you, it's composed of relations or tables. Each table has a name. For example, in this figure, you will see that the name of this relation is student, and it has a lot of rows. These are the rows or tuples. Each one contains a set of or has values that correspond to a set of attributes. These are the attributes: name, social security number, home, phone, address, office number, age, GB. All these are attributes which are actually columns. So the attributes and tuples of a relation student constitute this table. It could be in mathematical terms written like this. R, which is relation, is a combination of different tuples denoted by T1, T2 until Tm. That means more than one row or more than one tuple. In the relational model, we have also some attributes like a domain. What is a domain? A domain is actually a set of atomic values. What does that mean, a set of atomic values? It means a set of values that are indivisible. That means when you have, for example, in the previous example, we have this society number. It's a value that is indivisible. You cannot divide it. You cannot break it up, or a phone number or address, or like this. In some cases, you will hear about another concept called composite attribute, in which an attribute can be divided into many different attributes, like address, for example. If I can divide up the address into many different attributes, like the street number, the city, the country, the zip code, house number. So I can actually divide it. But once I divide it and it becomes an attribute, then at that time it will be indivisible. So each attribute, after it has been set as an attribute, the value of this domain cannot be divided. And each domain has a data type that specify each one of them. So, and a format, for example, a phone number. If you put a format which is could be followed as part of the design requirement, if you put it in this format, then when it is entered in the database, it has to follow this format. For example, a GBA, if it has to be written like this format, then this is an example of it. So one number before the dot, before the period, and two numbers after that. Or a date, for example. If it is the day first, then month, then year in 4 digits, and the month in 2 digits, and the day in 2 digits, then it has to follow this format. So it has to specify some kind of format or a data type. A data type could be a number, it could be a character, it could be a date, or any other data type. A schema is another concept that we can explain. Relation schema R is denoted by R. So the relation or the schema also is another concept that is used for the whole database, relational database, which shows the big picture of the database, the big picture of the mini world, is denoted by R, A1, A2, A3, and so forth, such that R is a relation name, and A1, A2, A3 are the attributes that make up this relation. And the attribute, it's actually, its name will imply the role it plays in the domain. So, for example, in the previous example here, if I have a name, that means the role it plays, this attribute, the role it plays in this relation is the name of the employee or the name of a student. And then home phone. So if I put home phone, that means it is not a mobile phone, it is a home phone. It has to actually, the values inserted in this attribute also denote or imply the role it plays in that relation. The degree of a relation is actually, by the degree of the relation we mean the number of attributes of its relation schema. That means this one, for example, there are 1, 2, 3, 4, 5, 6, 7. 7 different attributes. So the degree of the relation is, this is the number of attributes in that specific relational schema. And also, as we have seen in the previous figure, that a relation or a relation state is a set of n tuples. N tuples means more than one tuple, more than one row. So a relation is constituting more than one tuple, or more than one record, or more than one row. But R here is not for row, R here for a relation, and T is here for tuples. So simply these tuples inside the relations, they are usually making up the whole number of rows that make up this relation. And some of these values could be set as null value, which actually is also considered as, you know, a value that doesn't exist at this moment, but can be provided later at a later state. The mathematical relation of a degree n of the domain A1, A2, A3 is actually a subset of what we call a Cartesian product of this domain, such that the Cartesian product is actually the number of records or rows in one relation then multiplied by the number of rows of another relation. So if I have like these 3 different relations, and I would like in the set theory to make up all combinations, all possible combinations of these values that can be extracted from these 3 different relations, I can say that the all possible combinations are 27, which is 3 multiplied by 3 multiplied by 3, such that I can actually have A related to 1 related to A and to B and to C, and then like this: 1AD, 1AE, 1AF, again 1A, 1BD, 1B E, 1BF, and then you come to here to 2. Also it has 3, 2AD, 2BD, 2BE, and again 2 2BD, 2BE, 2BF, and so on. So you have 27 different. Usually it is a subset of the whole values provided by that Cartesian product of the domain. So it is a subset of that. So R, or relation, is a subset of the domain values multiplied together, all possible combinations of all values that can be extracted from such relations participating in that relation. The cardinality is the total number of values in the domain. So cardinality is all values that can participate in this domain. Cardinality has another concept that we'll be learning later, which is, we call it the degree cardinality, which is the relation with the relationship of a specific entity with other entities. And for example, if we have a team, football team, and we have the relationship between a team and players. Players is an entity, and a team is an entity. So the cardinality here, we say every football team has 11 players. So the relationship, the cardinality here is 11. That means total number is 11. So no less, no more. So because there is no more than 11 players that can be participating in the pitch at that specific time. So the cardinality is the total number of values in that domain. The current relation state specifies the relation state at a given time. So it actually reflects only those valid values that at a particular time that is available when they are uploaded for the first time or inserted. So the database state or the relation state constitute the current state of the database before it has been modified or changed or maintained or evolved or improved. So any state that was there is considered to be the valid state. We call it the valid state or the current state of the database. An attribute name indicates a different role for the domain. But usually in database, the domain name, the attribute name reflects its job. So by implicitly, database designers and users, when they read the name, they know the task or the role of that attribute in the domain. As I mentioned before, when you see, like, for example, a GPA, okay, this one is actually only you can enter the GPA, which is numbers, for example, in this record value. When you see a date, registration date, for example, only date can be inserted in that specific spot to play the role of the date in that attribute. There is a lot of characteristics of this relation that we can talk about here, which is we can say that the order of tuples in the relation, the order of tuples. That means if we'd like to order does the order of tuples in the relation a big deal? We can say no. Elements, there is no order among themselves, or there is no need to order them, or any order of these tuples cannot change the relation state. Let me give you an example here. Going back to this figure here. So what I mean here, these are 5 tuples constitute this student relation. So in any order, if this person comes in the beginning or in the middle or at the bottom, it doesn't make any difference. If this one in the middle comes in on top or in the middle or at the bottom, it doesn't make any difference. So the same values, because where you are changing the order, you are not changing the order of one single attribute. You are changing the order of the whole record. So all record, for example, this one, Benjamin Bayer, with his social security number and phone and address and age and GPA will be shifted down or up. So the order is not a big deal of these tuples. So ordering of tuples in a relation have no order or is not of any importance as such. Ordering of values within a tuple and an alternative definition of a relation. So order of attributes and values is not that important as well. Again, the same example can be provided here, which is the order of these attributes. If the office phone comes here before the home phone, or if the age is coming after or before social security number, or any change here happened, is not going to be of any importance, because when I'm shifting these attributes, each one of these values will correspond to specific value in that tuple. So the order of attributes and values is not that important, as long as the correspondence between attributes and values are maintained. So there is no any problem with that. we can say that a tuple is considered to be a set of attributes pairs. So they come together, they go together. So you cannot actually break them up, because each pair will give the value of the mapping of these attributes with their values in the domain. So there is this definition can be actually added to the characteristics of the relation, and this ordering is important when we use some applications like structured query language to extract values from the database, from the tuples in the database. So we can actually use some sort of commands to order them according to our liking. But as far as their existence in the database, they don't make any big deal to the database itself in terms of consistency. Here we'd like to talk about values like multi-attribute values, composite attribute, and so forth, and null values. So composite and multi-value attributes are not allowed in a flat relational model. Composite attribute and multi-value attribute not allowed in the sense that if there is a composite attribute, it has to be broken up. It is not allowed in that sense, but it is not recommended. I have to say, in the relational model, it is better instead of a name to have first name, middle name, and last name. For example, here this name here, Dick Davidson. So this will create a problem, by the way, if I have to implement it in a database design. Why? Because if I would like to search by last name, it's going to be very difficult to extract a specific attribute because there is no last name here. There is a name, which is a full name, but there is no last name. If I would like to search, for example, by the area code here, so this one could be a composite attribute. It can be divided into phone code and normal phone address also. If I would like to search by street address, a street name, not the apartment number, only by street name. So I will find some problems because there is no street name. There is address, a full address. So I would say this name, home phone, address, and office phone, all of them can be said to be a composite attribute. That means an attribute that can be further divided into other attributes to make our life easier for searching and retrieving data from the database after we implement it in any database management system. So we have some tools in database design called normalization to fix this problem, because every relation could be in its first normal form, but we can take it to a second normal form and a third normal form, and a third normal form is a final form that we can purify and maintain such relations so that we can have a better database design. Also, multi-valued attributes can be represented by separate relations, because if we have an attribute that has multi-valued, like color, for example, color attribute, color of a car. If I put just color of a car, okay, and then I happen to have a car that has many colors, it has a white, black, and red, for example. White, black, and red. The color is painted with 3 different colors, okay? So what will be the value of that attribute? It will be 3 different colors, black, white, and red. So in this case, it is better to be represented by separate relations, or by separate relations, such that, or separate attributes, so that we can have actually to put color 1, color 2, color 3, for example, so that you can have an indivisible value in every single cell. Because multi-valued attributes sometimes will create a problem in the database by having them, by writing them in the database and storing them in the database in that sense, separated by commas or separated by anything. So a composite attribute represented only by simple component attribute in basic relational model, and it could be, as I said, divided further into more than one attribute. Also, null values can be values of some attributes that might not be known at that time, or might not be available in the tuple. A null value is a value that is not known or not available or does not exist, but should be represented by the concept or by the term null. 0 is not a null. 0 is a number, but a null is a value that that can be represented by null, which also might create some problems in database implementation when we try to use these null values in calculations, because null value will provide null. Let me show you an example here. So, for example, if you look at this example here, you will see that I have used SQL here to show you this value 100. I would like to add 100 to 0. What is the result? If I add 100 to a 0, you should expect that 100 plus 0 is 100. Here it is. This is the result. But if I use the value null, N-U-L-L, what will be my value? It should be 100, right? Because null is not available, nothing. But unfortunately, you will get this, which is nothing. So if you would like to use a null value in database, the database in database null can create a problem unless we use some sort of tools also that can help us to skip this or take care of the null values in the database by using some functions like not null functions or something like that. So attributes does not apply to this tuple known as a value that is undefined or unavailable. There is some interpretation or meaning of a relation by using some characteristics like assertion or predicate. What is assertion? Assertion means assurance that each tuple in the relation is a fact of a particular instance of the relation. So every single value in the tuple actually constitute a value of importance. Predicate also means values in each tuple interpreted as values that satisfy predicate. What does that mean? It means values in every tuple has to abide by a condition that evaluate to some sort of Boolean value when I use some uh, tools to extract data or to maintain data. So it will, these values can evaluate to Boolean value. So either they exist or they don't exist. So the condition should be either true or false. So predicates can be used in a select statement, for example, where the where clause can determine which rows are relevant to a specific query. For example, look at this example here. If I would like to select student ID and section ID and major and GPA from the student table such that the GPA is more than 3.75, okay? This example means I would like to display to my screen these 4 attributes, but on the condition that the GPA exceeds or equal to 3.75. So what is the answer for this? The answer is either true. True means it will provide all those students with this GPA, or false, that means no student satisfy this condition. So predicate is will be interpreted by a condition that satisfies this sort of a condition that has been used in the database. So this notation is very simple. Use R for schema, use capital letters, use lowercase for relations. What is the difference between schema and relation? Schema is a whole thing. And for example, the college schema has student, course, section, prerequisite, instructor. This is called, all of it is called college schema, for example. Or hospital schema. Hospital schema, it has relations inside it, like a doctor, patient, nurse, pharmacist, and staff, something like that. And if we use letters like T, U, V for tuples, these are just notations that you can use them in design. They are recommended to use this kind of notation when you are actually designing a database. The name of the relation schema, for example, schema called student, indicate the state of tuples in that relation. So we have to, for example, think about it like this. If we have, for example, a student as a relation, then capital letter outside with the name of that relation, and inside you have to write the names of the attributes. And also attribute an attribute A can be qualified with the relation name R to which it belongs. That means every relation can be denoted by the attribute that belongs to that relation. And if we have, for example, name, attribute called name, but we have it for 2 different attributes, for 2 different relations. We have a relation called the student and a relation called instructor. But both of them have names. Both of them has phone numbers. Both of them have addresses. Both of them they have IDs. So how do we qualify such relationship between these attributes and relation names? So we have to use like r.a. And r.a means student.name. Student.name means the name of the students. Or I.id. That means the ID of the instructor. So because we're using this concept of what is called object-oriented database terminology, we will be able to map or to join the attributes that belongs to a specific tables or relations. some of the attributes of some of the concepts of relational model are called constraints. The constraints are restrictions on the actual values in the database state. These restrictions they are derived from the business rules of that database. So some of them, they are implicit constraints. Implicit constraint that they come with a design in the data model itself. For example, I would like to mention that the maximum characters you can put in a name are 25 characters. That is a restriction, isn't it? Another example, the data type of a student ID should be alphanumeric. Alphanumeric means alpha and numeric. This is restriction. Characters and numbers. Another example. For example, I said the date format has to be month first, then day second, and then year. Year should be in 4 digits. This is a restriction, because if you put year in 2 digits, it will give you some sort of violation in the database when you try to insert values in it. So there is some inherent model-based constraints or implicit constraints. Implicit constraints, that means implicitly come with the design. And schema-based constraints or explicit constraint can be expressed in the schema of the data model itself, as I mentioned, but there is also some sort of business rules, what we call application-based or constraints or business rules. These business rules indicated by some sort of rule that you express them in the application itself. So they are expressed and enforced by application program. For example, I have a grade for a student, like a quiz, and I would like to enter the grade, and then I actually have a rule there says the grade of quiz should not exceed 10, and the maximum is 10. So if I would like to enter 11 in the quiz, then I will get a message or warning or error that I cannot put more than 10 in that. Or value cannot be negative. For example, it should be more than 0. Also, if I enter something in that grade, it will give me a warning. Or a company that decided as part of the business rules that the salary should not exceed 15,000 reals. So if somebody would like to enter values in the database and he enter, for example, 16,000 for the salary for this specific employee, he should get a message that no more than 15,000 real should be inserted in this value. Why? Because in the business rule, you decided to have this restriction. We call it constraints. We call it application-based constraint, or semantic constraints, or business rules. This is implemented in the application itself, but it's not part of the schema based constraint. It's not created implicitly with the database. Some domain constraints can be the data type, which could be numeric for integers and real numbers, or characters, or booleans, which is true or false, or it has fixed length strings. That means address, for example, can be maximum 35 characters. So this is also constraint. Or variable length constraints. Variable length constraints also could be specifically written to have limitations. Date, time, stamp, also money. What to use for money. It has decimal places, it doesn't have decimal places, and there is a lot of different data types that you guys will learn later in the subsequent chapters, that you can get to know all different types of data types of these attributes. Also, there is something called key constraints. A key constraint, which is simply a unique value that specify the rest of the records, so that no two tables or rows can have the same you know same values or same combination of values for all their attributes. I mean, not typically the same. There should be something different for them. For example, I have two students who are twins. They have different names. They are living in the same address. They are having the same major. Everything the same, but there is some differences between them. At least the student ID of them is different. So I can have two typical products, everything the same, except that they're two typical products. That's, for example, coffee. Coffee, they have the same price, they have the same everything, and there is only difference in their item number. When they scan it on the machine, on the till machine, they get different prices because they have different flavors or something like that. So simply a key constraint there should have what we call super key, which is in which no two distinct tuples in any state of a relation can have the same value of this super key. Super key is a primary key usually, which is a key that uniquely identifies the rest of the records, which satisfies two properties. So two distinct tuples in any relation cannot have identical values for all attributes in the key, and also you cannot remove any attribute and still have the same uniqueness in the condition above. So you cannot have them as null. You cannot have a primary key that is null. A candidate key is a key that can be set as a primary key. Yani the relation can have more than one primary key. It can have more than one candidate key. For example, in your case, as a student, your student ID and your national ID, both of them are candidate keys. So if we take, for example, your student ID to be a primary key, then that will be called a primary key, but the other one is still a candidate key. Your national ID is still a candidate key. A candidate key is a unique value in the relation. A primary key is a unique but should be underlined, because if we underline it, then we will know that this is actually has been chosen to be a primary key. For example, here we have the car. A car has two different candidate keys, like license number and engine serial number. Unique, everyone unique. That means no one of them is repeated. But the one that is underlined is considered to be as a primary key. Although this one also could be a primary key, but it is not underlined, so it is not a primary key. It is a still candidate key. So, but these cannot be the same candidate keys. Why? Because once one of them can repeat in the value, then it is not satisfying the rule of a candidate key. A candidate key, usually a primary key is selected from among candidate keys. So this car relation has two candidate keys, the license number and engine serial number. But license number here is selected to be a primary key. So again, this mathematical term is now very simple for you to know which is a relation is composed of a set of attribute, and the schema is a set of relation. S for schema, R for relation, A for attribute, R here for relation. Relation 1, relation 2, relation 3. So the example for this one, relation student, for example, student name, student address, student GP, student something like that, major. But this one is a schema which is a big picture of the whole concept, which is, for example, a college schema, college schema, college equal student, course, course, section, instructor, something like that. All right. So a schema is a group of relations. A relation is a group of what? Of attributes. Okay. Here we can talk about invalid and valid state of database, in which we can talk about these concepts in the sense that invalid state is a state that does not have integrity constraint applied to it. So it is not taking into consideration all constraints or business rules that we have specified in our database design, while a valid state satisfies all these constraints in set of the integrity constraints. IC stand for integrity constraint. Simply, invalid state is a state that violates our constraints. Also, these two concepts are very important, which is entity integrity and referential integrity constraints. I would like to make it simple for you. I would like you just to understand that entity integrity means every entity or relation should have a primary key. This is a constraint. Yani every entity or a relation or a table should have a primary key. If it doesn't have a primary key, it means it doesn't have entity integrity. With the referential integrity constraint, it means that usually referential integrity constraints refers to relationship between two entities or more. So in referential integrity constraint means values that has been specified between two relations should maintain consistency among these tuples in the two relations. What does that mean? It means if you have, for example, employees working in 4 different departments, then these employees, no one of them should work in a department out of these 4. Every single department has to match specific number of employees. So you cannot insert a new record in the employee table unless the department for that specific employee is found. Or in this college example, we have, for example, in our college, we have a computer science department, mechanical engineering, civil engineering, and business administration. So when a student registers, he will register in this one of these available majors. So no student can be registered in a major or department that doesn't exist. And for example, there is no way that a student can now be registered in electrical engineering, for example. Why? Because there is no department of electrical engineering. So there is referential integrity. Referential means it refers back to the available related values in the parent table. Yani the parent table is a table that joins or make the relation existing between the two tables. In the department and employee, the department and employees tables, the department is the parent table and the employees is the child table. In the registration and majors or departments, the department is the parent table and the registration table is the child table. So no child will exist unless the parent is existing. That is the referential integrity constraint. We will explain it in more details in our next chapters as well. Foreign keys. What is a foreign key? A foreign key, just going back to what I have mentioned before about these examples, a foreign key simply is an attribute that that is a primary key somewhere else. So a value of the foreign key is actually not part of the specific relation, but it comes from another table to create such kind of relationship between the two tables. And for example, if I have employee table, and in this table I have an attribute called department number. Department number is not actually part of the attribute that describe the employee, but its existence in the employee table is just to make that relationship between the department and the employee. Also, if I look at the registration, I can say registration date, registration time, registration course, registration whatever. But when the department name is mentioned in the registration, which is not actually basically part of the registration attribute, that it is not a property of the registration, but why the major number or the major name or the department name existing in the registration? Because it has to make that relationship between the registration table and the department table, so that we can have such kind of relational or the relationship between the two entities. Such key is called a foreign key. A foreign key. Foreign, like the word foreign means, is coming from another table. So simply, a foreign key is a primary key in another table. It is existing here to create the relationship between the two tables or between the two entities. So that foreign key is actually helping in the referential integrity constraint, because if there is no foreign key in the child table, there will be no referential integrity between the two tables. So all integrity constraints should be specified on relational database schema because of this foreign key constraints. There is other types of constraints like semantic integrity constraint, which can be like triggers and assertions. These two concepts are some objects, database objects. Like for example, trigger is a specific object that will be created in a database that will fire when a specific event occurs. So when you try to make delete or update or insert on a database, for example, and then there is a message comes up, and these restrictions or constraints are created to be fired or to be executed at certain time or at certain event, when a certain event happens during the database processing. And also there is some constraints like functional dependency constraints, in which for example, which attribute depend on another attribute. Sometimes you will find in the same relation attributes dependent on another attributes. So without the existence of these attributes, this attribute will not be available. And this dependency is mean that, for example, value of x determine a value of y. So that means y does not exist if x is not there. So this functional dependency constraint establish this relationship among two sets of attributes, and they are dependent on each other. In other words, one of them is dependent on another one, or two of them can determine one, or one of them can determine two. So this kind of dependency is called functional dependency. And also there is state constraints, which defines the constraint that a valid state of database must satisfy. State constraint means the state of the database at a particular time. What is the state of the database? So these constraints also can be implemented in database design. Also, there is a transition constraints. Transition constraint when the database change due to specific processing or transaction. So the transition constraints define to deal with the change in the database throughout the database processing or during execution of specific transactions. There is also some concepts relating to update operations, transactions, and constraint violations like these operations that can be either grouped into what we call retrievals or updates, because any insert in the database could be regarded as change. Any delete in the database can be regarded as a change. Any update also is a change, or modify is a change. So these operations also they are in addition to what we can call retrieval, like select, for example, or select from specific values from specific tables. This also can be regarded as operations. So these basic operations that change the database could be called DML, as data manipulation language, as we will see in the next slides. It's called DML, database manipulation language, or DQL, like data query language with retrieval, or DCL, like data control language, in which you are actually creating some tools to control the database access or permissions. So all these are actually operations that can be dealt with in the database relational database system. This is a database for a company that have these three relations, which is employee, department, and department location. Also, actually, I have another three here, which is work on, project, and dependent. So I have 6 different relations or tables: employee, department, department location, and works on, and then also department, dependent, and project. If you look at them, you will see that the names of these relations are employee, department, and department locations. What are the attributes? Each one has a set of attributes. Look at the attributes of the employee, which is first name, middle name, last name, social security number, birth date, address, sex, salary, social security number, department number, and also the department attributes, which are department name, department number, and so on. Any one that is underlined, like this one, is a primary key, and here is department number is a primary key, and here this one together will constitute the primary key. Why? Because one of them is not unique. For example, here you will find number 5 repeated, but if you put them together will not be repeated. Each pair will not be repeated. That will be considered as a primary key. But most importantly, you will see the relationship between employee and department. If you look at department number 5, you will see that this one here, department number, exists as a foreign key, right? Because that means department number 5, which is research, has these 4 employees working in it, and department number 4 has these 3 employees working on it, and department number 1 has only 1 employee working on it. So the relationship between department and employee is a one-to-many, such that one department has many employees. The department number here is a primary key, the department number here is a foreign key, and so on. And here also, this one is a primary key or part of the primary key, which is composite key here, and the department number by itself also is considered to be a foreign key. Why? Because it is existing here as a foreign key, but it is a primary key here in this department table. So this relationship terminologies will be discussed further in the next chapters in more details. But this is just shed lights on how the relationship between relations can be seen. Okay. Also here, the relationship between the dependent and works on. You will see that here is a primary key, and here is part of a primary key. Part of a primary key. That means two of them here, dependent name and employee social security number together. They will make up that primary key. And here, project number is the primary key on this one. So project number is the primary key here on this one, and maybe if it is found somewhere else, it will be also considered as a foreign key. So anyway, this is a schema called company schema. It was composed of a lot of relations. These relation names here on top of these tables. And every relation constitutes of many attributes. Every attribute has its own primary key, and some of them they have foreign keys. The schema can be created in a schema diagram like this, in which you will see these arrows pointing to the foreign keys. Yani, for example, here is a primary key. This is pointing to the primary keys, but coming what? This is a foreign key. And if you take any arrow, for example, this one is a primary key, project number, but it is found here with a different name. So you can change the name, no problem, but the value is the same value. So project and works on relation, that means one project can have many project numbers. And also here, for example, one department can have many department numbers here because we have many employees working in it, and so forth. So this kind of diagram is called schema diagram, which constitute the referential integrity between the relations. And there is a relationship constituted by these arrows, because every arrow here is actually constitute a relationship between two relations. If you see the social security number here in the employee table, this social security number is a primary key, but it is found in 4 different relations. It is found in the department here. Manager social security number is values that has to be one of these values, because a manager is actually an employee. And also it is found here in this dependent. Dependent is a child or a wife of that employee. So if the social security number of the employee is here, then it is also found here in the dependent, because if there is no employee, there will be no dependent, and so forth. So these operations we talk about, I would like to just finish up with these last 3-4 slides talking about the operations, DML operation, like insert operation, which actually constitute a new table or record that will be inserted in the database, and if it violates any type of constraint, then there will be some sort of messages displayed for the user who enters these values. So if in any insertion violation found, then there is some rejection of this insertion. Okay, and the delete operation also can violate referential integrity, because simply if a tuple being deleted is referenced by a foreign key from other tuples, it cannot be deleted. And you cannot delete the parent and leave the child, and you cannot delete a department, complete department, and leave these employees who are working in that department. So if you'd like to delete a department, then first remove those employees who are working in that department, then come and delete that department. Okay, so for example, they would like to close a major for civil engineering, completely department civil engineering, but they would like to how do they just delete that civil engineering? They cannot just delete civil engineering. First, they have to remove those students from that civil engineering and move them to another department, like mechanical engineering or another department. Then after the department is empty, then they can delete it. So there are some restrictions. So the database management system will reject the deletion if such violation has occurred. And this cascade also. Cascade means you can implement some cascade operation in the sense that if you delete some values in one relations, automatically the values on the related the referenced in the related table or relation should be automatically deleted. Also, null values, some violation can happen in the null values if you try to insert nothing in the primary key. So there are some messages or violation that will be displayed to you in case you did not insert a value of a primary key. And you have to in the update operation, you have to select only the values that you would like to update. Otherwise, you will create some sort of inconsistency, because you have to select, for example, a primary key of such values. And for example, if I have here, I would like to, for example, delete from student where student name equal Ali, for example. Okay, this one I would like to delete student. No, his name is Ali. Just one second. Delete from student where student name equal student name equal Ali. What does that mean? I would like to delete the student, his name is Ali, from a student table. Okay, because he is no longer in that course. So this will delete all students with this name in the college, unless I use something different. Instead of student name, I use student ID, and then I write the ID here, because this one will delete only that student and leave other students with the. So I don't use the name, I use the ID, which is a primary key. This is what I mean here when I said you have to choose the primary key, so that you can have a correct deletion or a correct update on the table. So you can delete any value, but you have to specify some certain condition to be modified by using that primary key. Okay, and then the last thing we'd like to talk about is the transaction concept, which is transaction is something that you execute in the program to include some operations. And when you do a transaction, you must leave the database in a valid state or consistent state, so that either all transactions are done or none is done. For example, you are transferring money from one bank to another. So this transaction has to be fully completed, right? Because the money has to leave your account and get into the other's personal account. It cannot just leave your account and not get into the other, a person account and be lost in the middle. So it has to be a complete, it has to be executed as a complete transaction and leave the database in a valid or consistent state. And also the online transaction processing systems which execute transaction at rate that reach several hundred per second. That means if somebody, for example, is reserving a ticket to travel to a specific place, if this one cannot be done immediately and quickly, then somebody else in another place might reserve the same ticket, same seat, to another passenger, another customer, and this will create some sort of inconsistency and problems. So it has to be executed at a rate that it's called several hundred per second, so that it will leave the database in a consistent state. So this is the last concept that I wanted to talk about, and this one actually conclude our coverage for chapter 3.